This is MAT 175, Lesson 17, Section 5.3, Exponential Functions. And we're going to begin with evaluating exponential functions. To start with, we're going to review some fundamentals with exponents. Here when we multiply the bases, here we have, and we're going to add the exponents. Here we have a to the s parentheses to the t power, where I'm going to multiply the exponents. Here we have ab to the s power, so that breaks down to a to the s times b to the s. 1 to any power is just going to be 1. And then here we have a to a negative exponent. We're going to apply that becomes the reciprocal of that exponent. 1 over a to the s is the same thing as 1 over a parentheses to the s power. And then anything to the 0 power is 1. Okay, we have here a basic equation for an exponential function. We have some number c times the base a, and then we have our exponent is a unknown variable. And so with an exponential function, the x variable is an exponent. And so that produces some special problems that we have to deal with. And so that involves working with these types of problems in a little bit different way. Alright, so here it shows that c, when x is 0, c is going to be basically where we have when x is 0, that will be the y-intercept. In other words, it shows that, so if x was 0, it would be at, the intercept would be at c instead of at, so if c was 1, if this is like 1 times whatever this base is here, then that's going to be the intercept, the y-intercept is going to be at 0, 1. And so here we have a graph that shows anything with a negative exponent. If we put a negative exponent here, like 2 to the negative 1, then that would be 1/2. And then if this was, as the negative value gets large, as we get more and more negative, then the y value gets smaller and smaller. So that shows that here in the table of values. But once it hits the y-intercept, it's always going to go through at 0, 1, as long as c is, as long as there's nothing multiplying times this base. And then from there, whatever your base is, 2, in this case, this one's 2, then at 1 it's going to be that y value 2. So if this was 5 to the x power, then this would be 1, 5. So you get that vertical stretching from whatever your base is. And so 2 to the so when x is 3, you get 2 to the third, and that's 8, and so on. So you get this exponential growth type of a pattern. And notice here, we have a horizontal asymptote at y equals 0. So we can say that this is our parent graph for f of x is 2 to the x power, with our horizontal asymptote at y equals 0. Notice that between our y-intercept and the horizontal asymptote, that's one space. And it's always that way as long as there's not some number multiplying the base. And this is just a representation of a graph that shows an exponential growth type pattern. If you were to put points through the midpoint of each one of these boxes and then draw a line, you'll see you get an exponential growth type of a pattern. And so that's just a real world type of a example. Here we have y equals to 6 to the x power, and so when x is 1, you get 6 out, and so this would be 1/6. And so whatever your base is, that first point after the y-intercept is going to be 1 in that number. And here this would get smaller and smaller and smaller. So on the left side, that'll get smaller and smaller and smaller and get closer and closer and closer to that horizontal asymptote of y equals 0, but it won't cross. For these graphs, these graphs here will not cross the horizontal asymptote. So here we have f of x equals to a to the x, where a is greater than 1. Then, in other words, our base is greater than 1. Then we're going to get our, it's going to intercept, it's always going to intercept the y, the horizontal, the vertical, or the y-axis at 0, 1. And whatever this base is, at negative 1, it'll be 1 over that base. So if this was, let's say, 3 to the x power, then this would be 1 over 3. Negative 1, 1 over 3. And then this would be positive 1, 3, and so on. Okay, so now if we have a fraction like this, where a is between 0 and 1, then we get what we call exponential decay. And so when x is negative now, like negative 1, you're going to flip that 1/2 and you get 2 out. So at negative 1, you're going to get 2. And negative 2, it's going to, here at negative 2, it's going to flip and you get 2 squared is 4. Negative 3, you get 8. So you get this exponential decay as x becomes more positive. Again, it's going to intercept the y-axis at 0, 1, and now as x becomes more positive, then you get that fraction. So like at 1, you're going to get 1/2. X is 1, y is 1/2. And x is 2, so that'd be 1/2 squared, that's 1/4, and so on. It gets smaller and smaller and smaller, gets closer and closer and closer to that horizontal asymptote at y equals 0. And that's known as exponential decay. The other one, that's known as exponential growth. Alright, and so here's the two together. Now if you have y to the x where you have a, back up here, x to the negative power, then what that does is that reflects the graph about the y-axis. So here's y equals 2 to the x power. So y equals 2 to the negative x. You get that reflection. It reflects about the y-axis. And you could also write it as a fraction, or as a rational base of 1/2. Either way, it's going to show that reflection about the x-axis, or about the y-axis. And so here, this shows that 1/3 when x is 1, y is 3. For 1 over 6 to the x power, when x is 1, y is 6. So basically when you have that negative 1, it's going to flip it. And so that's why you get, when x is negative 1, y is 6. Here, if this is a negative 1 power, x is negative 1, it's going to flip it, and you get 3 out. Okay, and so this basically represents the same thing. So when a is between 0 and 1, in other words, a fraction, then you're going to get this exponential decay. And you're going to get that intercept, again, at when x is 0, y is 1. So whether it's positive, you get exponential growth, or exponential decay, you're still going to get that intercept going through at 0, 1. And see, notice, again, even with exponential decay, you still have 1 unit from your horizontal asymptote to your y-intercept. Okay, here we have a graph. And just like with transformations, with any function, the same thing happens here. You're going to get transformations that occur the same way. So let's say that we had f of x, just as a review, equals to x squared minus 3. Well, here's y equals 2x squared, right, before any transformations occurs. So this is going to make it shift down 3 spaces. So here, you start with the parent graph of y equals to 2 to the x power, and basically you got that horizontal asymptote at y equals 0, and that's going to go through at 1. Well, because this is negative, it's going to cause the graph to flip about the y-axis. So you get this y equals to 2 to the negative x, and so now it's going to come down like this. It flips about the y-axis. And again, but this is still 1 here. Now, and your asymptote is still at y equals 0. Now it's going to your transformation is going to go down 3 units. So now with y equals to 2 to the negative x power, you're going minus 3. It's helpful to start with the horizontal asymptote. So the horizontal asymptote starts at 0. So that's going to go 1, 2. The horizontal asymptote will go down to y equals a negative 3. And notice that since it's 1 unit, right, this will be at negative, it'll intersect the y-axis at negative 2, because this will go 1, 2, 3 units. So that's at negative 2. So this comes down like that, goes through at negative 2, and then it just rides along that horizontal asymptote. So when you graph these manually, you're going to have to graph the horizontal asymptote. You're going to have to graph showing that the new y-intercept is now at negative 2. And then you're going to have to show that it's exponential decay. Okay. And so there's y equals 2 to the x, the parent graph. And then it switches about the y-axis. And notice here's y equals 0. And at this point, the horizontal asymptote shifts down to negative 3. So you always want to start with the horizontal asymptote, because that's going to help you out. And so see, you always have that 1 unit from the horizontal asymptote to the intercept, to the y-intercept. Oh, and one more thing is that here you still have that left one up, that would be 2. So this would be, in this case, this would be left one up 2. So this is 0, negative 2. And so that would be left one up 2. So, alright. Now here, E. E is a number. This is the basic equation for E, where E is a limit of n that tends towards infinity. You have 1 plus 1 over n to the n power. So basically, you're not going to have to know this. This is just, sometimes people ask, well, what is E? Well, E actually has an equation. But all you need to know is E is basically rounded off to 2. It's an irrational number, or actually, in this case, 2.7. E basically rounds off to 2.72. So when we have e to the 1, that's 2.72, and so e squared is 7.39, and so on. So it's still, even with e, you still have a horizontal asymptote at 0, it comes through the y-axis at 0, 1, and then at 1 it's going to be at 2.72 for the y. And so here, when you have the negative out front, this is like saying that just like with y equals to a negative x squared opens down, okay, we have this f of x equals to e to the x, and so we get this exponential growth. Here's 1, and here's your horizontal asymptote. Well, when we have f of x equals to a negative e to the x power, that's going to flip about the x-axis. So now instead of intersecting here at 0, 1, now it's going to intersect at 0, negative 1. You're still going to have the horizontal asymptote at y equals 0, but now you see how this gets closer and closer and closer to the horizontal asymptote, but it never does touch it. Well, it's still going to get closer and closer and closer to the horizontal asymptote this way, and you see how after it hits 0, 1, it goes up. Well, here when it hits 0, 1, it's going to get more negative. Y is going to get more negative. And so from here, now this, x minus 3, like that, comparing it to x squared, that would be like x minus 3, close parentheses, squared. So that's going to make the graph shift, and you should have said, it's going to be down, open down, but it's going to shift which way? You should have said to the right 3 spaces. And so that's what's going to happen here when we have f of x equals to negative e to the x minus 3. It behaves like it does when x is in parentheses. So that's going to make this point here, the y-intercept, it's going to make this point shift. So here's your horizontal asymptote at y equals 0. So it's going to make this y-intercept shift 1, 2, 3 spaces. So now, instead of being here at x is 0, y is negative 1, now it's going to be here at x is 3, y is at negative 1. And it's going to ride along the horizontal asymptote, and then once it gets to 3, 1, then it's going to break downward. So your new y-intercept has shifted 3 spaces to the right. So I'm going to be looking for that. Where did that y-intercept shift to? And in the transformation where it flipped about the x-axis. Okay, and so that's what it shows here. Here's your parent graph, and it reflects about the x-axis and then shifts to the right. So here's your 1, 2, 3. Here's your new y-intercept. It shifted from 0, negative 1, and that went 1, 2, 3 spaces to over here. And that's what this is. Okay, so this would be the new y-intercept right here. Alright. Solving for exponential equations. Okay, so if you have a base to some power equals to the same base, and it's a different power, then what you do is you just set the exponents, or the powers, equal to each other, and then you can solve from there, if you have to. So, in other words, if we had, let's say, 2 to the second power, and that equals to 2 to the x power, then what we can say is x equals to 2. And that's what that's saying there. Okay, so here we have a problem where we have 2 to the 3x minus 1 power. So if we can get 32, if we can change that to 2 to some power, then we can set the exponents equal to each other and solve. Well, in this case, 2 to the 5th power is 32. So since we have the two bases are the same, we can set the 3x minus 1 equal to 5, and then we set the exponents equal to each other, and we can do away with the bases, and now just solve for the exponents. And so we add 1, and that gives us 6, divide by 3, and that gives us 2. Okay, here we have, now this one presents a different problem because this is going to be, first we take this 4, these two exponents we can multiply. So we can say this is e to the negative 4x. Alright, and so what we can do at this point is we can say, since this is e to the negative 4x and this is e to the 3x, we can subtract the exponents. So basically what we're doing at this point is, back this up a little bit, is we're taking this e to the 2x minus 1, and so this becomes e to the negative 4x over e to the 3x. And we know that when we have x to the m over x to the n, we're subtracting exponents. M, first exponent, minus second exponent. And so that's what we're doing here. This will be e to the 2x power minus 1 equals to e to the negative 4x, first exponent, minus second exponent. And so that'll give us e to the 2x minus 1 equals to e to the negative 7x. And so now, since the bases are the same, we can just set the 2x minus 1 equal to negative 7x, and then from there we can solve. Okay, and that's how we got to this point here. So we got e to the 2x minus 1 equals to e to the negative 7x, and then from here we can solve. We get x equals to 1/9. So in summary, we have, when a is greater than 1, we have exponential growth. We have y equals 0 as a horizontal asymptote, and you're always going to get that intercept at 0, 1. And so at 1, it's going to be 1, and then the y value be whatever that base is there. For a base that is a fraction between 0 and 1, you're going to get that exponential decay. Again, your horizontal asymptote is at y equals 0. And then at negative 1, it'll be negative 1, and then whatever that reciprocal is. And your domain is going to be negative infinity to infinity, and your range is going to be from the horizontal asymptote on up to positive infinity.